Why, hello, and welcome back again to a whole bunch of fun stuff with position, velocity, and acceleration. What this lesson is going to be about today is this is going to be about not about the graphical nature of position, velocity, and acceleration. It's going to be about the function work that is involved with position, velocity, and acceleration. So the first thing I would like you to do is you should have a piece of paper that looks like this. I would like you to stop the video now, and I would like you to reread this front page, making sure that you are looking at the formulas and the function work that goes along with each of the major things. So stop your video now and read through those things. Now, the big thing we're going to do today is I'm going to try to organize, if you look on the back here, I'm going to try to organize this idea of position, velocity, and acceleration into some sort of graphic organizer for you. And so we're going to use this as we kind of start doing some function work. It's going to all be in one sort of place. So what I'd like to start with is I would like to kind of start with the function notation for each one of the things that we're going to be working with. So when we start, position usually is S of t, okay? S of t, where t equals time. Now let me present my window because I think you probably want to see that. So position is S of t. So velocity is V of t. And the thing you always need to remember is t is representative of time. So t equals time always. And acceleration is equal to A of t. Now, there are some sort of connections between all of these. And so what I would like to do is I would like to kind of draw some graphs and kind of help you see some connections between each of these things. So let's draw in a graph for a position function. So we're going to start with our position function, and position function always goes like this. The time is right here. Your S of t value, or position, is on the y-axis, okay? Now, with position, you can have, you'll have some sort of graph or things like that. So I'm going to just kind of draw a position graph here. So I'm just going to pretend that our graph goes kind of up and goes down, and then it goes up again like this. So it's kind of like some form of an x cubed function, okay? So the first thing that you do need to realize is you do need to realize that there's a connection calculus-wise between position, velocity, and acceleration. So that's the first thing I would like to note. So if I gave you some sort of function, and let's say I called that function y, or I called it f of x, or something like that, okay? So we call it that function, whatever it might be, and we'll define it as something. There is a connection between the position and the velocity. That connection that you need to note is you do need to note that it is the derivative. To figure out velocity, you have to take the derivative of the function. Okay? So what is the notation for each one of these? Well, velocity would be y prime, or it would be f prime of x, or it would be dy dx, and then of course you would have some x value, but you would be taking the derivative of each of those things. Now, there is a connection between velocity and acceleration, and that connection is that it is the derivative of velocity. Okay? So when we think about that, what it is it's actually the second derivative of the original function. So we do y double prime. Or it is the second derivative. So it's f double prime of x. Or it is d2y dx squared. That means to take the derivative of at x equals some number. So it's going to be one of those three things that we will see. So as we're kind of going through this, you need to understand the notation of how this works. Okay? So if you have the position function, you take the derivative of it to find the velocity at a spot. If you have the velocity function, you have to take the derivative of that then to figure out what your acceleration is. Okay? So let me clear this out of there. Now, what I'd like to do is just make sure that it's focused because it looks a little blurry to me. Okay, so now, what does that mean graphically? Okay, so what does it mean graphically? Well, graphically, we'd have to, if we had this function here, let's go ahead and let's draw the derivative of that function. So still, time is always going to be on your x-axis, but if we're now going to draw the velocity graph, v of t, we have to do a couple of things. So remember, I always told you, if you have a graph like this, to draw the derivative of it, the first thing you should do is you should mark where you have horizontal asymptotes that are equal to 0. So about here and here, I have, horizontal asymptotes, which are not horizontal tangents, horizontal tangents that are 0. So I'm going to mark those two spots on my graph. Now note, if we look before this dot, it is a positive slope. So if I draw little tangent lines, it's positive slope, but it keeps getting less and less. So I'm going to start up high, and then I'm going to go down low. Okay? Now, this is positive slopes. This section right here, what is happening with the slope? Well, the slope is less, it's starting to go negative, then it gets more negative by the time we reach here, and then it gets less negative as we go right here. So we start positive, we go down, then it gets negative, but then it gets less negative, and it has to move back to 0. So this middle section is a little dip in the line. And then the last part is it goes straight up like this. Okay? So the derivative of this graph looks like this. Remember, this is the derivative of the position function. Now, remember, this is an x cubed graph. This looks like an x squared graph. So what do you think the last function is going to be? Well, if we go like this and we take the acceleration graph, so it's still going to be time, except we're going to have a of t here. Notice we have one spot that it is equal to 0, and that's right here. So if you notice, there is a horizontal tangent right there. So we're going to mark that on this graph. But now notice, the slope is negative, and it's getting less and less and less negative. So this graph needs to, and I'm going to have to jump down here, it's going to start way down here, and it's getting less and less and less negative till we reach the point where it is 0. Then it gets more and more and more positive, and so it goes up like this. Notice, this is the graph of a line. And this is kind of how it always works. Okay, remember, when you take the derivative of it, you're always subtracting 1 degree from the exponent. So this is an x cubed-like graph. We then go to an x squared-like graph in the shape of a parabola, and then the last one is the shape of a line. So you do need to remember, though, that we are taking the derivatives of each. Okay? So in words, what is position? Position is your location with respects to a starting point. Respects to a start. Okay? So you're always going to have some place where you are starting, and it's going to be your location. That is what position is. Okay? Now, velocity is how fast you go in a certain direction. So if you remember in the previous video, I told you that velocity does have a direction component. If velocity is positive, it means it's moving in a direction towards the right, okay, towards a positive direction. If velocity is negative, it's moving towards the left on a line, which is a negative direction, okay? Now, what is acceleration? It's how much your velocity is increasing or decreasing. Okay? So this is the idea of speeding up or slowing down. Okay? So that's what acceleration is dealing with. It's this idea of speeding up or slowing down. Now, what I would like you to now do is we are going to talk a little bit about some formulas that are really, really important, okay? And then we're going to do a problem together. So let's take a look at this idea of displacement. Displacement is it's how far are you from a certain point. So if I were to give you any sort of graph, and let's say the graph just kind of goes like this and it winds around, and I was to ask you, you know, here is point A. So this would be S of A. And then here is point B. This would be S of B. I just want to know how far apart you are in total. Now, what that means is that just means I need to subtract these two things. So displacement is S of B minus S of A. I just want to know how far are you from your start to your finish. Okay? And it's always that formula. It will always stay the same. Now, average velocity then would be, if we use this same graph, average velocity would be the slope between these 2 points. It is the slope between S of A and S of B. So we would do S of B minus S of A all over B minus A. Now, the final thing that's really important is you do need to know what speed is. And speed is the absolute value of velocity. Okay? So what you would do is you would take the absolute value of whatever your velocity function is at a certain point. So it also would be, or it would be the absolute value of the derivative of your position function. Okay? So either one of those would be acceptable. So let's go through and let's kind of apply